Okay, so I think a lot of people are back from the break, so let's just get started. So today we have the pleasure of having Prateek Jain giving us a talk about learning from dependent data. Prateek is a research scientist at Google Research India and an adjunct faculty member at IIT Kanpur. Earlier, he was a senior principal researcher at Microsoft Research India. He obtained his PhD degree from the Computer Science Department at UT Austin and his BTech degree from IIT Kanpur. He works in the area of large-scale and non-convex optimization, high-dimensional statistics, and ML for resource-constrained devices. He wrote a monograph on non-convex optimization in machine learning. Prateek regularly serves on many program committees of top ML conferences and has received many awards for his works. Most recently, his work on alternating minimization, being selected as the 2020 best paper by the IEEE Signal Processing Society. So without further ado, let's welcome Prateek.
Thanks, Greg. Thank you all for attending the talk. And thanks to the organizers for having me here and for this wonderful event. Only one small suggestion. Please don't slot anybody after Mike Jordan's talk at least for 2 hours. Let people just look at and think about those amazing results and marinate in them a little bit. Anyway, so let's start with this talk where I will discuss some of our recent work on learning from dependent data. This talk is based on joint works with some amazing collaborators, including Dheeraj and Praneeth, who have done who have contributed some amazing ideas to this work. So let's first set up the problem itself. So we know machine learning models are now very popular; they are used everywhere, and if you think about it, how we learn these models, well, we are given some input X and we want to find some parameters W so that on some test point coming from some fixed distribution, the output of the model for input X almost matches Y, right? And to enforce this fidelity, we have this loss function, which will try to sort of make sure that model is learning something where the loss for a given data point X is fairly small, right? So how do we optimize this or find these parameters W? Well, what we do is we sample a few points from the distribution and minimize the loss function, right? And generally, in machine learning, at least big part of machine learning, we assume that this data is sampled independently from a fixed distribution D, right? But in practice, this might not hold in a variety of problems, especially around, say, reinforcement learning, online learning kind of problems, where let's say you have some kind of agent working with an environment, agent takes some action, AT, environment, and we are in some state ST, and we get some reward RT for that. So this tuple is what we will need to learn, right? That is, we are in some state, we take some action, we got some reward. But once you took the action, now you are in some other state ST+1. And state ST and ST+1 need not be very far from each other. They might be very close to each other. So imagine that you are playing some move on a chessboard. One move will not completely change the picture unless you are grandmaster. So so your states are very correlated with each other, and that's why the model we cannot sort of optimize this assuming that all the data points are independent of each other. These kind of problems are quite common nowadays, especially with all these large language models, which are essentially modeling sequences. So there again, you would ideally want to take care of the temporal dependencies in the data. And another thing that we want to make sure here is that, because say in reinforcement learning, this is an online learning system. So we would want ideally stochastic gradient type of methods, which do not wait for the entire data to come through. You are getting samples of data, you're making some updates, and you are moving on. Now, typically, these stochastic gradient descent type of methods are studied in IID settings. That is where all the data points are independent of each other. But we want to sort of, now restrict it to settings where the data might have arbitrary dependence on, or might have dependency on each other. Now, in general, the problem is very, very hard. And especially if you allow for completely arbitrary dependencies, then it's almost a nightmare to model it. So many times people put this reasonable assumption, which is that the data is Markovian. That is, given current state or current data point, we don't care what happened in the past. Just that data point is what dictate the next data point. So, and this Markovian assumption again is is reasonable in reinforcement learning, time series estimation, and a variety of other settings. Now, in literature, there has been a lot of work with learning with dependent data. In particular, there has been a lot of work on taking these data points, doing some sort of offline analysis on it. And like, a lot of problems I study, like, say linear dynamical systems, where there is some system which is sort of generating this data and we want to estimate the system. But most of these work sort of studies statistical property of this dependent data. That, oh, if my data has this particular structure, what type of statistics I can get out of it. They are not focusing much on the algorithms to estimate these systems or properties of the system. Similarly, like so another sort of very interesting line of work that is going on is in the online learning community, especially there's very nice work on online control theory led by a lot of people, but Alad Hassan has been one of the primary drivers here. And here again, there is a lot of focus on algorithms, but that the data might have worst case tendencies. That is there might be some adversary who is sitting and giving some fairly challenging data points for you. In this work, we want to sort of go somewhere in the middle. That is, we are saying that, okay, we will have some fixed system from which we are getting this sequence of data points. And what we want to do is estimate the parameters of the system in an online fashion. And this sort of system is useful even for, say, modeling large scale training. So for example, if you are training your largest language model, at least in IID setting, you might have trillions of tokens that you have to train on, and you are not going to sort of run multiple times over those tokens. You are going to just take one pass over that data and give you some output, right? So this sort of stochastic approximation setting is fairly popular in IID setting. It is used in practice quite a bit. But with temporal dependencies or with sort of this Markovian type of dependencies, the problem has not been studied a lot. There has been some interesting work by Chaba and Shrikant and Ying, but by and large, a lot of sort of fundamental problems in this space are not very well studied, and that's what we'll try to do in this line of work. So this is sort of the outline of the next 40 minutes or so. So what I'll do is I'll start with a very sort of brief warm-up of linear regression problem in a streaming or stochastic approximation type of setting. But I'll start with the IID setting. That is, the data is independent. Let's just understand what are the key parts or key components that come out of the problem. And then we'll try to see if those ideas then apply to, say, linear regression with Markovian data and some other settings. So this is sort of roughly the setting in which we will be working. So you have some data points, xt, yt, sampled from some fixed distribution. Unlike sort of the latest ML worlds where people are dealing with 100-layer networks and whatnot, we will deal with 1-layer network, which is a linear regression network. So we will assume, or we'll try to model our target yt as a linear function of the input xt. The parameters are given by some vector w. And for simplicity for now, what we are assuming is that yt can be written as in a product xt with some optimal parameter w star plus some noise, where this noise is independent of the data and noise is coming from some Gaussian distribution with standard deviation sigma. And for simplicity for this slide, we'll also assume that, let's say, the data point itself is coming from some Gaussian distribution. So it's really, really simple setting. So for this type of setting, we want to sort of optimize this least squares error. Right, so this is the expected loss or expected error that we want to minimize. And there has been a bunch of work on this this problem, and people have got very precise information theoretical bounds. In particular, you can say that if you have sort of t points in d dimension with this sort of setting, then you can estimate w up to this error. That is, compared to the optimal error, you will have an additional error of sigma square d by t. That is, this error scales linearly with the dimensionality as well as inversely proportional to the number of points that you are seeing. And you cannot do better than this in general. This is sort of the optimal thing. Now, how do we sort of achieve this information theoretically optimal bound? Well, at least up to constant factors, you can do that by using this very simple idea of tail averaged SGD. So you start with some initial point W0, which is, let's say, for simplicity, let's initialize it to 0. And then at each time step, you are getting one data point from the distribution. You run one stochastic gradient descent update with some step size eta. And after that, after sort of running it for, say, t by 2 steps, what we'll do is we will store all the remaining things, all the iterates, and we'll just take in tail average of all the iterates. of the last t by 2 iterates, and that gives you the final sort of thing that final output, right? Now, one question is how do you set the step size? Well, theoretically, at least you can set it something like this, that is some constant divided by the norm of the largest vector that you see in this tree. All right, so what do we get for this? So for this problem, for this linear regression problem, we can analyze this tail SGD fairly well, and we can get precisely the type of error terms that you'll see. So generally, in this kind of situation, the error can be divided into two parts. One is what we call bias. So bias you should think of as that initially you started at some point W0, which was far away from W star, right? So depending on how far W0 in from W star, that term is what we call bias. So bias term basically is dictated by your initial point, right? And what this analysis says is that bias term is decreasing exponentially fast in T. That is, in number of points, it is going down exponentially fast. That is, and in particular, this kappa is a sort of conditional number factor. So what this sort of says is that as soon as you are larger than as soon as you've seen more than kappa points, your error decreases very rapidly, and it's almost minuscule. Now, there's one more term here, which is what we saw in the information theoretic bound, which is that there is some kind of variance term due to the noise in the system, which comes here, right? Because remember, in our observations, there was some sort of noise with standard deviation sigma. So that's the term that comes up here, right? So we are approaching this information theoretic bound at an exponential rate by decreasing this bias using this tail averages. So this is what basic result says here. Let me give you a very quick sort of overview of how these analysis is done. This is important because as we build upon these to go for Markovian data, independent data, I want to highlight precisely where some of the existing techniques will get stuck and why we need to sort of come up with new techniques, right? So if we look at bias analysis for SGD, for simplicity, let's assume that there is no noise in the system. That is, YT is given by exactly in a product of XT and W star. So no noise, right? So here, the SGD update looks something like this. WT plus 1 is equal to WT minus this gradient of 1 point. And if you subtract W star from both sides, then you essentially get a term like this, right? So this term is interesting because what this sort of says is that the error at the T plus 1th step is essentially error at the Tth step times this matrix, right? And as long as we can ensure that this matrix is positive definite, we will be decreasing error, right? Like the norm of the error will go down in each step. So that's all you want to do. Now, there's a little bit more work here because this is just WT plus 1 minus W star. We want to prove this statement for the norm or norm square of these vectors or norm of the error vector. So for that, you need to do a little bit of more linear algebra work. But bottom line is that as long as your step size is smaller than 1 by the largest norm of the vector square, and as long as your Hessian is given or like the covariance matrix, which is expected value of your XX transpose, as long as that is strictly positive definite, you'll be fine. Like you will be able to reduce this error at a fairly good rate. Right. So now the second term that we were talking about is the variance term. That is also reasonably easy to analyze. Obviously, putting this proof together requires a little bit more effort. But if you think intuitively, like what variance says is that even if you're at the optimal point and you start doing gradient descent around it, or stochastic gradient descent, you will not stay at that point. You will sort of, have some kind of perturbation around that point, right? And we want to, like the variance term essentially captures how far you can move away from that optimal point, right? So, for that, for that analysis, let's just sort of say that suppose I was at point W star, I took one gradient descent step, so that sort of adds this much of noise, right? Like eta xt epsilon t. And then, when we look at WT plus 1 minus W star square, in expectation, it looks something like this. Like it basically eta square sigma square trace of the covariance or the Hessian matrix, right? And then because we are taking now tail averaging, which means that these terms are essentially getting averaged. Like all these are noise terms. Like here, this epsilon t is IID noise. So we are just adding these, let's say n by 2 or t by 2 points together. Like we are averaging them out. And that's why that error drops down significantly. And that's what this like 1 by t kind of term you get. This is actually an expectation statement, but we can get high probability statement here. That's not very hard. So any questions about the bias and variance analysis here? Yeah, go ahead. The issue is that when you use full averaging, then this bias analysis, you cannot use that easily because you are averaging all the terms. So because of that, like this exponential rate that you're getting, you cannot get that. There is a very nice work by Francis Bach and his students where they show that if you do full averaging, then you will get something like 1 by t square here. And that I think is a real term. That is, if you don't do tail averaging, just full averaging, it's not just an analysis. Even in practice, you will see a rate to become. Tail averaging is in some sense optimized. We haven't optimized, like we just said, let's take constant fraction of points. I think you can probably do a little bit better. There's a little bit more sort of, nuances that you can introduce here. So you can say that, okay, rather than like, taking 1.8 each time and then just taking the tail, what I'll do is I'll start taking some batches of data points. And initially my batches of data points will be very small. So I will have batch size very small, but then as I go through those small points, I know that I am decreasing this bias term quite significantly. So in the later part, I will mainly just take bigger batches of data, run one gradient descent step in and do tail averaging. So that then can give you slightly better rates. But yeah. Anything else? So this is like, the how picture, at least like, that we understand in the setting of linear regression with this very simple IID data assumption. So in deterministic case, you have some sort of log 1 or epsilon convergence towards the optimal solution, where this term is multiplied by this condition number kappa GD. Kappa GD you should think of as the condition number of your Hessian matrix itself, right? When you do SGD, then you have very similar term, plus the standard information theoretical variance term anyways will stay for all of them, but you will be able to converge to at least good point at this rate. But the kappa that you have here can be almost order D larger than the kappa that you have here. And that is the price that you have to pay for processing only one point at a time, rather than your entire batch of points at a time, right? Now, in the deterministic case, or when you're processing this entire batch of data points, you can use this acceleration technique. So you can use this momentum methods or Nesterov's accelerator method, and you can reduce this dependency on kappa to root of kappa, right? And that then sort of, raises this interesting question that can you do the same for SGD also? Can you get some sort of accelerated version of SGD? And in setting, we show that, yeah, it is possible, but the picture becomes a little bit more nuanced. That is, you will have some root kappa term here, but there is some sort of statistical property of the system also that comes in picture. I will not go in detail there, but this can be done, right? Another sort of interesting thing here is that, that we are sort of saying that one pass SGD is nearly optimal, but our rates are now almost in some sense dependent on D. So one can say that, okay, what if I want to get smaller rates by taking multiple passes? Is it possible? So in general, no, but in certain cases, yes, it is possible. That is, if your dimensionality is very, very high, and there are some special property or geometry in your data, then you can get faster rates than this. Again, if you're interested in this, there is some very interesting work by Francis Bach and his students. You can take a look at it, right? So this is the picture for ID data. Before going to Markov thing, let me see how much time I have. Yeah, so let me give one sort of, quick flavor of results that such results can enable. So so for example, by using pretty much this idea, we were able to get nearly information theoretical optimal bounds for making linear regression differentially private, right? So this is just to recap the situation. That is, we want to estimate this W star, and we can estimate it only up to this error of sigma squared D by N. Here I'm using, you can think of T also here. And we want to now do it with differential privacy. That is, we want to say that if my data set differ by 1 point only, then my output probabilities should not differ by a whole lot, right? That is, if there are two data sets D and D prime, which differ by at most 1 point, then with a very high, actually this statement is wrong, but what you want is that for any set S, the probability that algorithm sort of gives to that set S, or the output belongs to the set S, should pretty much remain the same. Like that one data point should not change the output of my system quite a bit, right? And again, like linear regression has been studied a lot in differential privacy, and people obtain like this type of rate for linear regression. So here, if you look at the rate, this is our information theoretically optimal term, but this is the term that you get because of privacy, right? And here, like there are two key issues. One issue is that if you look at this rate becomes non-trivial only when the number of points is much larger than d, right? Here you have only an n square term, but here you have a d cube term. So you want your number of points to be larger than d to the power 1.5, and then only the rate becomes meaningful. Whereas without privacy, we just needed number of points to be larger than d. So that's one gap. Another sort of gap that comes here is that even if sigma is 0, right? And I've seen say more than d, or let's say even d to the power 1.5 points, still I'm not getting 0 error. I'm not able to get the optimal estimate of the differentially private thing with 0 error. Like I'm still paying some more error because of privacy, which seems non-intuitive. Like why should that happen? So in this work that we did with my collaborator Abhradeep Thakurta and Prateek Vashne, we said that okay, let's try to use our results on this IID linear regression and try to see if we can modify our algorithms for that purpose, right? So by doing that, what we are able to do is we are able to get this rate which seems nearly optimal, right? That is the rate now has terms like d squared by the number of points squared. So as long as the number of points is larger than d, then the rate is meaningful. Another thing is that here now the dependency is only on sigma. That is, if sigma is 0, then we are saying that, and if the number of points is larger than d, we are saying that we will be able to estimate the optimal solution even with differential privacy, like point blank, like without any error, right? So, and the algorithm is fairly simple. All we do is we use the tail average SGD algorithm that we have and do some more sort of adaptive clipping on top of it. I will not go in detail of that. That's not most important. I just wanted to sort of highlight that this kind of stochastic view of linear regression can be useful in settings other than like the core problem, like even in differential privacy and all, it can be quite useful. So let me skip this. Let's now come back to our main topic, which is least squares regression with Markovian data, right? So our setting is that our data points are coming from some Markov chain, and say we have some observations y is equal to this data point x transpose w star plus some noise, and the goal is to minimize this least squares loss, and we want to focus on SGD and its variance, right? So, so first result that we have in this phase is actually not very positive. So the first result sort of says that in the general case, when we are not making any assumption on the noise, then the loss of any estimator will be larger than this term. So let's look at this term carefully. So here, there is this very important factor, which is tau mix, which is essentially the mixing time of your Markov chain. So intuitively, mixing time of Markov chain is the amount of steps you have to take before your data points look almost independent to each other. That is, let's say you have data point x1. When you look at x2, x2 will be very, very similar to x1, right? Like you can estimate a lot of things about x1 maybe by x2. And similarly, x3 will be very close to x2. But as you're going along, like, x4 probably will be less similar to x1 compared to x3, right? So as you're going along, after about tau mix steps, the data points will look almost IID. That is, they will look almost independent of each other, right? So that is called mixing time of the chain. Mixing time obviously depends on chain to chain. Like, some Markov chains might have very good mixing time. Some Markov chains might have like, very poor mixing time. So let's say if there's Markov chain, which is basically just repeating the data point one after another, like the same data point is being repeated again and again, it has mixing time of infinite, and you won't be able to do much there, right? Because you're getting one data point. How much can you really estimate from one data point? But on the other hand, if your data is almost IID, that is, your mixing time is essentially 1, then you will be able to sort of estimate things very nicely, like almost apply the same IID theory, right? So here what we are saying is that the error again can be broken into this bias and variance term, and both the bias and the variance term have to pay a penalty because of this mixing time. So the variance rate of decrease have now, it has slowed down by this factor tau mix. And similarly, your variance has increased by this factor of tau mix, right? And this is a information theoretic bound, that is, you cannot hope to do any better than this. Okay? And in fact, for general settings, there are some Markov chains where if you apply SGD, at least with constant step size, then it might not even converge. So SGD is not a really good solution for these kind of problems in general. But you can do one very, very trivial algorithm, which is what we call SGD data drop, where basically what you're doing is you're saying that, okay, I know my mixing time is tau mix, so I will take every tau mix sample. So I took sample 1 plus tau mix, sample 1 plus 2 tau mix, and so on, right? We know that those points are almost independent of each other, so we'll be able to solve our problem. But that will get pretty much the same rate, right? Like this is pretty much the rate that you'll get out of that. Yeah. Well, here when I say converge, it's not converging to the optimal solution. Like it's not unbiased. Any other question?
Distribution, right? So
yeah,
you mean the average, tail average?
Tail average, yeah. Yeah, so maybe there are a few more things here, but yeah, generally let's think of this result with SGD with constant step size and tail averaging, and in that case, we are talking about convergence. Yeah. That's a good point. So there are some methods that can allow you to estimate tau mix. So you will need to waste some samples, but initially what you do is you just wait for your points. You do these tau mix estimation things, and then you say that, okay, now I know that this is my tau mix, and based on that you run. In practice, you wouldn't probably do that. You will just sort of have some estimate of the mixing time, or you maybe start with some larger mixing time. And then as you are going along, we'll try to decrease it to so that the things are looking reasonable. Estimation, if you're, ideally we will need estimation. Yeah.
You say not even converge. What do you mean? Is it?
No, so, well, here we are talking about Markov chain that has a finite mixing time. But this SGD is not arbitrary SGD. This SGD is SGD with constant step size and let's say with tail average. So for that particular setting, we are talking about convergence. So what happens is that when you're running this SGD with constant step size, you have, let's say, 2 points which are very correlated with each other, right? So your SGD completely sort of, goes in that direction. Like it is not learning anything, almost anything from those data points. And that becomes an issue. And then you can sort of fool it like that. Any other question? Okay, so this is the first result, which says that, okay, if general case, you cannot hope to have much more than doing this very trivial SGD data draw, right? But suppose we make our problem a bit easier. Remember, the target YT is given by inner product of XT with some W star plus this noise eta t. Suppose this noise eta t is independent of the samples. In that case, we can show that the information theoretic lower bound has the same bias term, that is the bias is still slower by this tau mix factor. But now the variance term does not have the tau mix factor at all. So at least lower bound that we could get, it does not have this tau mix factor. So one can say that, okay, suppose if I again did your tail averaged SGD trick with constant step size, do you get the optimal variance? Well, unfortunately, it turns out that you still don't. That is, your variance is still larger than tau mix by t. So standard SGD with constant size is still not a good idea for this problem. But you can run a much smaller, a simpler, or sorry, variant of SGD, which is what we call parallel SGD. The idea is very, very simple. What you do is you keep, let's say, tau mix parallel versions of SGD. That is, on the first sample, you run first sort of run of SGD. On the second sample, you start your second run of the SGD. Third sample, you start your third run of the SGD, and so on, right? So here, let's say your tau mix is 4. So you will have these 4 parallel versions of SGD, right? And so first version, like after it has processed x1, y1, it will go to 1 plus tau mix point and process that, and then 1 plus 2 tau mix point, and so on. And similarly, second version will process the first point, or the second point, sorry, and then the 2 plus tau mix point, and then 2 plus 2 tau mix point, and so on, right? So each of these parallel versions of threads of SGD, they are processing these points independently. And after that, what we do is, like, once they have done this processing, we will average all those runs, right? And that we are able to show. You can sort of, after that, you can retrieve the optimal rate. So here we will do tail average and then average of all the SGD runs. Yeah. They don't communicate with each other. Yeah, only in the end we are doing averaging, which then sort of explains why we are not getting any benefit in the bias term, right? So in variance term, sure, you will get benefit, because if you are very close to the optimal, then there is anyway just noise. So we are averaging all these runs, so we can hope to get rid of that tau mix factor. But the number of samples that each chain or each SGD is seeing, SGD instance is seeing, is now 1 by tau mix factor of the total number of points. So you cannot hope to do any better. Like even in IID settings, your rate will be this tau beta, T by tau mix, if your number of points that you're seeing is T by tau mix. So you cannot hope anything better here. So this sort of says that, yeah, I mean, we can get the optimal rate, but still there's this annoying factor that, oh, we have not been able to decrease this bias at a faster rate. And it's a sort of natural question that, can you do something better? Turns out, yes. But so far, we are able to do it in, like, very, very specific setting. So there's this sort of Gaussian autoregressive process, or you can think of it as a Brownian motion. For that kind of process, we can get something better than what your trivial parallel SGD kind of algorithm gives you. So, let me define the model itself. So suppose you start with some point x1, which is sampled from, say, some Gaussian. Then point x2 is given by a combination of x1 plus a IID Gaussian vector g2. And similarly, xt will be given by a combination of xt minus 1 plus some IID Gaussian vector g2. Right? And this epsilon sort of, dictates what is your mixing time. Like intuitively, if epsilon is 0, right, then you are not moving at all from your initial point. So your mixing time should be infinite. And if epsilon is close to 1, then your mixing time is essentially 1. And that is what you roughly get. So this tau mix, you can sort of, view it as of the order of log d by epsilon square. This tau mix is not tight for large epsilon. This is only for epsilon, which is fairly small, like less than some constant. Okay. So let's see, like, for this particular setting, that is when my data is coming from this particular chain, and suppose I don't have any noise, in that case, will SGD again give me something? Because now my data is much simpler. Can SGD itself solve the problem? Unfortunately, it turns out that even in this case, SGD is not solving the problem. That is, SGD still have rate of convergence, like at least the bias rate of convergence, still have this tau mix factor. So not much we are getting out of SGD compared to simple data drop technique, which is just dropping almost all the points other than the tau mix points, or T by tau mix points again. And the issue that comes up is that when you try to analyze SGD, if you remember in the bias term, you have these terms like this that come, right? And when you had IID setting, then what we could say was that, oh, when you're taking expectation here, all these multiplications are independent of each other. So we could sort of bound each one of them separately. But now the expectation doesn't multiply here because all these are dependent on each other. So bounding this term becomes much more tricky. And what we basically show is that this term cannot be bounded any better than 1 by tau mix. So that's why you are not able to get much. Right. So can we do better? Well, we tapped into what people do in practice, and in practice, people use this technique of experience replay. That is, whenever you are running, say, Q-learning on some practical problems, practical reinforcement learning problems, you don't run a vanilla Q-learning method. You run that Q-learning method with some kind of experience replay. And people have come up with a bunch of variety of experience replay techniques. Here we will just look at one particular experience replay technique that is called, I think, uniformly at random experience replay. So the idea is very simple. You take a pool of points or a batch of points, and when you're running SGD, like, you will just go through them one by one, right? But here we are saying that we will not do that. We'll take this batch of points, and we will, for the next point from this batch, we will randomize, like that we will take 1 point uniformly at random, and we will feed it to SGD. So within a batch, we don't follow the ordering that was given. Within a batch, we are taking randomization, like, we are taking uniformly at random samples. And that then helps break these correlations that we had, right? Like earlier, the issue was X1 is, X2 is dependent on X1, X3 is dependent on X2, and the tight coupling was very hard to break. But now when I take a batch of points, and suppose the batch of points is reasonably large, let's say I have, say, tau mix points or so, then I can sort of break this coupling reasonably well, like by taking these uniformly at random samples. So that's the main one key trick. The second thing that we have to do mainly for analysis purpose, I think, is between these buffers or batches, we put some sort of gap. So this gap is how much? Well, we put a gap of about, say, tau mix, right? So this sort of says that, okay, for processing, say, order tau mix point, I am throwing out tau mix points. So I'm essentially throwing only constant fraction of points. Unlike this SGD data drop, where to process 1 point, I had to throw much larger fraction, like tau mix points. So instead of that, here you are sort of throwing away constant fraction of points. So it should not affect our rate too much. But this gap between these buffers help us in analyzing just these buffers individually, and then just taking multiplication across all these buffers, because these buffers are separated by tau mix, so they are essentially independent of each other. So we can apply the same machinery that we had for IID data across all the buffers, and within the buffer, we have to do a lot more work. So is the algorithm clear? Any questions about the algorithm? Okay, great. So yeah, so this we call SGD-ER, SGD with experience replay. Well, as I said, like, we didn't come up with the experience replay algorithm. The algorithm has been known for a long time. In fact, it was introduced in '92 and is widely used in RL. It is used in DQN, and there are a variety of variants of experience replay. But one thing, like, people have observed in experience replay quite a bit is that the batch size that you use for experience replay is very critical. That is, if you use too large a batch size, then you don't have enough updates. And if you use a too small a batch size, then that can bring so many correlations that you're not getting much out of it. And that is what our analysis also show. And yeah, like if you're replaying these multiple step experiences, there is some, like, independent experiences that also helps performance. But one problem with all this line of experience replay work is that there are no sharp rates of convergence. In fact, before our work, we were not even aware of any other work that analyzed any type of experience replay in any setting. So what do we get out of our analysis? So, well, assuming, like, this data model, and suppose we have noiseless setting, what we can show is that SGD with experience replay can drop the error at much faster rate. That is, now the rate of convergence depends on root of tau mix rather than tau mix that SGD has, right? So compared to standard SGD, now the error rate is dropping at a much faster rate. It is still not completely independent of the mixing time, but at the very least, we are able to bring that dependence down significantly. And we don't know, like, if we can do any better for this particular chain. Like, this is what we have right now. Right? That is, yeah, like, if you look at the rate of convergence for this sort of noiseless setting, this is where SGDER is, like, it will converge at much faster rate compared to sequential SGD. Right? Now, if we want to sort of, consider some sort of noise on top of the data, we can provide that analysis also. And the analysis has sort of, interesting form. So here, what we are getting is this faster rate of convergence with 1 by root tau mix rate, but we have to pay in variance. Like, in variance, we have one additional root tau mix factor. And one interesting question is that, similar to like parallel SGD, can we get rid of this root tau mix and still have this faster rate? Any question about this mean result? Great. So let me sort of quickly go over the proof, sort of, a key idea, like, that we have the proof. So as I said, like, across the batches, things are independent. So we are fine. Let's just look at within the batch, right? So within the batch, when we look at the error term, like especially the bias term has these matrices multiplied of this form, right? And because of this, experience replay, we know that these things are now, they can be thought of as IID, right? Like all these XTJ terms within a buffer, they are IID in the sense that they are sampled from one buffer in a uniformly random manner, right? So that then allows us to apply this expectation, and we get a term like this for that buffer, right? So we have a term like I minus 1 by B times XT transpose, where columns of XT are basically these vectors XTJ that we are processing in the buffer, right? So that's great. But we still cannot sort of, get the result with this because these columns of XT are all correlated with each other. So we don't know how to bound the norm of this matrix, overall this matrix, right? And for that, we need to do a lot more work. So one sort of key intuition is that the eigenvectors of your XT transpose matrix remains the same as your eigenvalues of Gram matrix. And here, like, the main issue is eigenvalues, that if you can bound the eigenvalues away from 0, then we will be able to show that it will converge, right? We just don't know how to bound it. So for that, we are saying that, okay, rather than considering the covariance matrix, let's look at this Gram matrix, which is X transpose X. And after that, like, we can exploit some structure here, which is that when you look at ijth entry of this matrix M, it has the form of Xi transpose Xj. And because we have a very particular Markov chain, we know that Xi transpose Xj has this kind of form, and in expectation we can bound this. And based on this, like, this sort of tells us that. So one sort of interesting observation is that Xi transpose Xj inner product has a form of this, term to the power j minus I. So it is not dependent on I or j. It is just dependent on how far element j is from element I. And that means that the Gram matrix can be written as a circulant matrix. Circulant matrix, we understand the eigenvalues very well. So we use the formula for eigenvalues of a circulant matrix. There's some noise on top of it that we need to take care of. But bottom line is that you can make this analysis work after doing a little bit of work, right? And what does this give us? Well, what it tells is that, so as I said, like the result is that we are able to converge at faster rate compared to standard SGD. And that is what we observe in practice also. So here you have SGD with data drop and SGD with like a standard SGD. And you can see that, the convergence starts to happen at pretty much the same point. But like at around d by epsilon square point. But when you look at SGD with experience replay, what we observe is that right at this point, which is about d by epsilon, we have convergence, our error starts to drop exponentially fast, which means that we start seeing that bias term kicking in properly. Okay. So this indicates that our theoretical analysis is also reasonably tight in this particular case, because this happens almost at d by epsilon point. So yeah, so key takeaway from this thing is that in general, we cannot hope to do much better than the standard bias rate that you get out of standard data drop. That is, if you are just looking at every tau mixed point and just running an SGD on top of it, that seems to give the optimal bias rate for even for this very simple linear regression problem. But if you are willing to make some further assumption on your Markov chain, so here we made a very particular assumption that our Markov chain has this Brownian motion property, then we are able to show that you can indeed improve SGD algorithms rates by introducing concepts like experience replay. Right? And this is sort of a summary of how things look. So basically, in agnostic case, we have these lower bounds where everything, like both the bias and variance, depends on tau mix. And that is what you can achieve with your very trivial data drop method also. When your noise is independent, the variance doesn't have the tau mix term, but the bias has. And SGD will like its variance will have tau mix term, so we cannot avoid like that term for SGD. But if you run something like a parallel SGD where you're keeping multiple versions of SGD, then we are able to get the correct variance term. And finally, if you're willing to make some more assumption, like if you have some sort of autoregressive data, Gaussian autoregressive data with independent noise, in that case, what we show is that SGD with experience replay method is able to achieve faster rates, both in terms of variance as well as bias. So that's all I have. Any questions? Yeah. Yeah. I'm sorry, can you come again? Yeah, you're right. I mean, like if we could make the batch size to be smaller or the buffer size to be smaller, then we could have hoped to get like faster rate of convergence also. But yeah, like that is what we could work out because the analysis was quite critical, like tricky. Like if you remember, like we had to map it to circulant matrix and some sort of noise is on top of there. So for this particular task, yeah. 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 So it is, but if you look at it, like the point at which it starts to sort of its error starts to drop, it's very similar. I'm not sure if this is mainly just some sort of constant fraction thing. That is, SGD is a bit better, but only by some sort of constant factor. That's not completely clear. Any other questions? So thank you. And I'll see you in 20 minutes or 15 minutes. 17 minutes.